So, today we shall discuss the performance of enzyme catalyzed reactors, the reactors in which enzyme catalyzed reactions are supposed to take place. You will recall earlier we had discussed some of the salient features of different reactor types ranging from batch reactors, batch stirred tank reactor to continuous stirred tank reactor or plug flow reactors and fluidized bed reactor. In fact, some of the unusual reactor configurations which have been proposed to catalyze to be used for carrying out enzyme catalyzed reactions like hollow fiber reactors. Of course, they also arbitrarily fall into one of those categories of plug flow or CSTR were discussed. We had also seen earlier the factors that affect the choice of different reactor types, and to recall some of the factors that we had talked about. The most important ones are listed here, like form of the enzyme, that is the soluble, fibrous or particulate, the nature of the substrate, whether it is soluble, particulate or colloidal, operational requirement, the control of pH in case an acid is produced or consumed in the reaction, reaction kinetics, the carrier loading capacity, catalytic surface to reactor volume ratio, mass transfer characteristics, ease of catalyst replacement and regeneration, reactor cost and ease of fabrication. Now, I think all these factors that I have listed here you can consider mainly under two categories. One category is the factors which become fixed once an immobilized enzyme is prepared. That means, the factors that essentially are dictated by the immobilized enzyme preparation itself. For example, form of the enzyme, the nature of the substrate is also fixed. I mean, once the enzymatic reaction is defined, the nature of substrate is fixed. The operational requirement is also fixed depending upon the nature of the enzyme catalyzed reaction, whether an acid is produced or consumed, and pH control is a requirement. Similarly, the catalytic surface to volume ratio is also fixed once an immobilized enzyme preparation is available. The carrier loading capacity also depends on the bulk density of the immobilized enzyme preparation and things like that. Then of course, ease of catalyst replacement and reactor cost and ease of fabrication are the factors which are dependent on the enzyme reactor, type of enzyme reactor. But the two important class of factors which I wanted to point out here, one is your reaction kinetics and mass transfer characteristics. Now, they are the ones which very heavily dictate the choice of the reactor, whether to go for a plug flow reactor or to go for a batch reactor or to go for a continuous stirred tank reactor are very heavily dictated by mass transfer requirement and reaction kinetics. Of course, I must again point out that the heat transfer requirement we have knowingly ignored, assuming that most of the for most of the enzyme catalyzed reaction the heat of reaction is very small, and so heat transfer during the reaction is not a major critical factor. Of course, in certain cases, if it is so, the heat transfer characteristics also must be taken into account. Then last time when we were talking, we had also considered certain idealized reactor design parameters. That means, for design of a particular type of reactor, what kind of parameters, design parameters are important, and you will recall that we had also sort of hypothesized certain conditions or assumptions which define an idealized enzyme reactor system, and the assumption were that isothermal operation, delta H is very small, uniform enzyme distribution, plug flow behavior or completely back mix behavior. That means, you have one of the extreme fluid dynamics in the reactor system, either it is a plug flow motion or it is a completely back mix, nothing in between. I mean there are, and that is what we have assumed, that, and there are no mass transfer limitations and no significant partitioning of substrate between bulk and the carrier phase. These were the basic assumptions which defined our ideal enzyme reactor. And of course, the reactor design parameters, that means the parameters which we should define initially before we go on to design any particular reactor, was tau, the space time in the reactor, initial substrate concentration, enzyme loading E0. Of course, in the case of continuous operation, the information about the deactivation rate constant is also required, Kd, then the temperature of operation, pH control, and the other design parameters are, these are essentially the reaction conditions. Other design parameters are fractional conversion and productivity and reactor capacity. That means, what is the maximum reaction capacity if assuming that the enzyme reaction follows a maximum reaction velocity, that is 0 order profile, and that is the kind of a reactor, the productivity of that kind of a reactor will be your reaction capacity. And of course, ultimately I think the performance will be dictated very heavily by enzyme kinetics. Now of course, again if we consider an idealized enzyme reactor, we can safely say that Michaelis-Menten kinetics provides us a basis for carrying out a universally acceptable kinetics for enzyme catalyzed reactions. And so therefore, we will assume in most cases V is equal to K2 E naught S upon Km plus S. Of course, wherever we are talking of immobilized enzyme, we must also clearly understand that these terms K2 and K dash M are noted by prime, indicating only that they are immobilized enzyme parameters and not the soluble parameters. Now coming to our the first and probably the most simplest reactors is a batch reactor. Now essentially, as I told earlier, the batch reactor can be used both for soluble enzyme as well as for immobilized enzyme. You can carry out a batch reactor in a stirred mode or in a packed bed mode with using total recycle, and on the right hand side is a characteristic profile of the reaction species, that is substrate and product with reference to time. The substrate concentration drops, and depending upon the extent of conversion which we require, and the product concentration increases. A typical profile, of course, it can change from reaction to reaction. If the reaction is very strongly inhibited by product or strongly inhibited by substrate, the profile might undergo a change. Now one of the probably a very general feature of analyzing reactor performance, as you may be aware, is material balance. Across the reactor, you take material balance for one of the reaction species, say substrate, and make a material balance, simplify it, do mathematical sort of steps, you will arrive at a reactor performance equation, which will give you the performance of reactor. When I say performance of reactor, I mean the extent of conversion as a function of resistance space time, or in a batch reactor with the reaction time. Now in the case of a batch reactor, essentially you will notice that the reactor performance can be judged simply by integrated form of the reaction equation, and that is minus ds over dt is given by K2 E naught upon Km over S plus 1, typical Michaelis-Menten equation. Now also even when we write the integrated form equation, we can assume that this is also valid in the case of if you make a material balance across the batch reactor, because in the classical material balance equation requires that your input minus output minus conversion should be equal to accumulation. Now here in the case of a batch reactor, the accumulation is volume multiplied by rate of change of substrate concentration minus, that is V ds over dt. Input and output here are taken as 0, because there is no continuous input and output, only initially we feed the reactor and at the end of the reaction time the output is taken out. So, there is no continuous, there is no I mean sort of say, output or input into system, and conversion is given by the rate of reaction. So, V into rate of reaction is your the total accumulation and the conversion factor, and by cancelling the volume term from both the sides you can arrive at the essentially the integrated form of equation. And this equation, if you solve, integrate it, you lead to the reactor performance equation essentially. Now, if you just simplify it, you will get your Km ln S naught upon S plus S naught minus S is equal to K2 E naught into T. Now, essentially again I would like to repeat that in case if we are using a batch reactor for immobilized enzymes, we should replace Km and K2 naught by prime terms. Otherwise, if it is soluble enzyme, the Km and Vm values are. Now, as I mentioned that we often describe the performance in terms of your, now let us say this is the equation 1, 2. Now, if we want to describe the equation in terms of reactor performance, then x is equal to S naught minus S upon S naught, which can be also written as 1 minus S upon S naught, or S upon S naught is your 1 minus x. So, if you substitute all these parameters, you get in terms of reactor performance equation for a batch reactor in the form of fractional conversion, that is K dash m ln 1 upon 1 minus x equal to K2 dash E naught into T. The reactor performance equation for a batch reactor in terms of course, here we must also consider that we want in the form of product concentration. Product concentration is nothing else but S naught minus S, assuming that it is a unimolecular reaction. That means 1 mole of substrate gives you. Now, if in case you are handling with a different kind of a reaction scheme, let us say 1 mole of substrate goes to into 2 moles of product, then accordingly one has to make a change in the the definition of x as well as p. Now, this will be also equal to x into S naught, and therefore, you can also write in terms of product concentration Km ln upon S naught minus p plus p equal to K2 E naught into T. Now, if you look at these equations, you can use the reactor performance data of a batch reactor. That means, you take a single batch performance data, that means take the fractional conversion at different times of reaction. You can write down the expression ln S naught upon S upon S naught minus S plus 1 upon Km equal to K2 E naught T upon K dash m S naught minus S. Right from the equation 2, if you just simplify, you get a straight line equation which can give you the values of your Km and Vm in the case of a now, if you plot, let us say ln S naught minus S upon S naught ln S naught minus S upon S naught minus S and T upon S naught minus S, you get with the slope of K2 dash E naught upon Km dash and with the intercept as minus 1 upon K dash m.
So, is it ln S naught minus S or ln S naught by S?
This is ls S naught by S, right, not minus S naught by S. So, you get now, in fact, this provides you one of the simple method, for example, when we immobilize enzymes, we always notice that if we monitor the sort of kinetic parameters Km and Vm, Now, I think the simple way to measure the kinetic constants for a immobilized enzyme reaction will be to carry out the reaction in a batch stirred reactor, monitor the substrate concentration or fractional conversion with reaction to with reference to time, and determine the parameters by single reactor performance data. That provides us a simple tool, a batch reactor for and in small scale laboratory experiments to determine the kinetic parameter, both for soluble enzyme as well as for immobilized enzyme. Now, here I must again put a caution. When we use the Michaelis-Menten equation, you will recall that we had made certain assumptions, and the assumptions were that we are talking of the initial reaction rate. That means at a time equal to 0, whereas when we integrate the equation from 0 to time t, let us say to a conversion, fractional conversion of 90% or 95% or 99%, the reaction rate is not likely to remain the same as that at the initial time. So, basically here we are violating some of the basic assumptions of Michaelis-Menten equation, but still it gives you a very approximate situation for designing a reactor or making some design calculations to work out a reactor size or the capacity of the reactor, accepting that, and of course you can compare between soluble enzyme and immobilized enzyme, but otherwise under idealistic condition, the assumptions in the Michaelis-Menten equation, that is of initial reaction rate, absence of product inhibition, is not met here. So, when we apply this the integrated Michaelis-Menten equation for looking at the performance of an immobilized enzyme reactor in the batch mode, we must keep that in mind, that it only gives you a approximate situation just to judge the sizing of the vessel, sizing of the required for a particular enzyme catalyzed reaction, and all to compare the soluble enzyme with that of immobilized enzyme, the performance. Now, here also if you look at under extreme conditions, we have always seen, even while looking at the kinetics of the soluble enzyme, we always look at the situation when it comes to extreme substrate conditions. That means either when the substrate concentration is much smaller than Km, or when it is much higher than Km, that means it ranges from first order to 0 order enzymes, how the reactor performance will change. Now, similarly, for example, when substrate concentration is much smaller than Km, your reactor performance becomes minus K dash m ln 1 minus x is equal to K2 dash E naught into T, and when S naught is much greater than K dash m, that is your 0 order enzyme, your x S naught is equal to K2 dash E naught into T. Now, basically I think we must also appreciate that if suppose you approximate an enzyme reactor to follow either a 0 order or a first order enzyme, knowing the values of Km and K2, the error involved in that will be determined by the ratio of Km to S0. Now, if the ratio of Km to S0 is very small, you will hardly incur any error if you assume it to be a first order, and you will see when we go on to consider along with the reaction kinetics, we will consider mass transfer and all more complications. We will tend to approximate our reactor performance in either 0 order or first order enzyme, rather than making it a Michaelis-Menten equation, which might make the solution of the expressions more difficult, or it can be done by numerical methods, but analytical solutions may be difficult. We basically make an assumption depending upon the the range in which our substrate concentration exists in relation to your Km value. So, basically the error involved will increase if you increase the ratio of Km to S0 and you assume first order, because then it will go more towards the 0 order kinetics. If the ratio of if the Km to S0 ratio increases and you assume a first order kinetics, your error will keep on increasing. Km is much smaller, sorry, Km is much larger than the S0 in the first order. So the value of Km upon S0
should be large.
Km upon S0 will be large, that's right. Km upon S0 will be large, and under that conditions you must assume a first order kinetics, and I mean if the value of Km to S0 decreases, the error will continue to increase. In fact, one can make a hypothetical computation to see what is the extent of, I mean I must also mention here that when we write in the beginning, then we take up an assignment to design an enzyme reactor or any, for that matter any process equipment, a 10% error in calculation is usually taken for granted. You know, there is no point in making an accurate classical science. Of course, if you are going to measure, let us say, the value of Km or Vm, you need an accurate value. But when you want to go for design, let us say reactor capacity, what is the volume of reactor required to carry out this conversion, you obviously you are not going to be very specific that this is the volume required. You will add on to that about 10% open head space or for various purposes. So if let us say if the error involved is less than 10%, I think there is no harm in making an assumption of 0 order or first order. If the error involved is much larger, then of course our assumption will be slightly hazardous. The next simple form of reactor system which is commonly employed is a continuous stirred tank reactor. Now, in the continuous stirred tank reactor, one is a continuous flow reactor, that means the volume of the feed, the feed rate of the substrate is same as the output rate of the product stream. So, if the feed is added at the flow rate of F, let us say liters or moles or per unit time, whatever units you follow, at the same rate it is the same amount. So, the volume remains constant. Substrate concentration S0, the substrate concentration changes at the exit, but one of the characteristic feature is that the substrate, all the parameters at the exit stream are same as in the reactor itself. That means the reaction will take place under conditions of S, P or X which exist at the exit stream, and therefore, if you just write a material balance for such a reactor system, you can write accumulation as V into ds over dt equal to F into S naught is the input minus F into S if S is the substrate concentration in the outlet, and minus V into V. V is the reaction velocity, that is the the conversion due to reaction, and V is the reactor volume. Now, obviously, if we consider that the after a certain period of time the reactor comes under a steady state situation. When we say steady state situation means that the concentration of any species does not change with time in the outlet stream, and under that condition the accumulation term will tend to be 0, because whatever material is coming in, either it is getting converted to reaction or it is going out of the reactor. There is no accumulation of any species in the system, and therefore, one can write your V is equal to d S naught minus S, that is equal to K2 dash E0 S upon K dash M plus S. Now, d is a term here what we understand as dilution rate or F by V, or in other words V by F is the residence time, the inverse of space time. So, this d is the term, and or you can write here, from here you can also write K2 dash E naught into S upon K dash M plus S, or K2 dash upon S, this is equal to S naught minus S upon tau, that is your space time that was defined in the earlier expressions. Solving this equation, you can also get K2 dash E naught into tau equal to S naught x plus K dash m into x upon 1 minus x. That gives you the reactor performance for a CSTR, and if you just again from the substrate concentration you make a substitution for your x, you arrive at the reactor performance for CSTR. And similarly, here also if you make assumptions of 0 order or first order situation when K dash m is much smaller than S naught, that is a 0 order system, tau is equal to x S naught upon K2 dash S naught. And for first order system where K dash m is much greater than S naught, you have K dash m x upon 1 minus x equal to K2 dash into E naught into tau. So, the two extreme conditions for the reactor performance can be judged.
So that will be x S naught by K2 prime E naught.
X which one?
Second expression.
Second expression x S naught upon K2 prime E naught, sorry, yes, that's right, not, you are right, E naught. And so you get the two expressions, rather I would say that for CSTR the general rate expression, general reactor performance expression, and also under conditions of 0 order and first order scenario, 0 order, first order. Now, if you notice that in the case of the expressions are very simple, and then if you have the data available for any reactor performance for S0 fractional conversion required, you can determine the volume of the reactor required or the feed rate required depending on the tau, and one can make computation to define the reactor performance under given conditions. Now, the other idealized reactor, or which is what we understand as a plug flow reactor, is slightly typical in the sense that unlike in the case of a CSTR, the concentration of the substrate or product varies along the length of the reactor. So, making a material balance across the reactor, you cannot choose any concentration term, because the concentration term for substrate changes with the length of the reactor, and the concentration of substrate or product is not constant throughout the reactor, it varies. And of course, this can also be assumed analogous to, that means if you consider along the length of the reactor kind of a batch reactor with different reaction times. But again, to arrive at the reactor performance, what we can do is we can make a material balance across a differential element of the plug flow reactor, and if you consider a differential element of volume dV, you can make a material balance under the same conditions like the flow rate, feed flow rate as F, the conversion changes from x to x plus delta x, at the inlet x is equal to 0, at the outlet x is of course some value. Now, then if you consider here input to the system is F into S, and this input I am writing at the entry of the differential element, and output not at the entry of the reactor is equal to F S plus del ds, and the disappearance of the substrate by the reaction will be the contribution of the reaction to the disappearance of the substrate is minus V into dV. Now, under these conditions one can write the material balance as input equal to output S plus ds plus disappearance by the reactor. Now, under steady state, assuming that the accumulation is 0, and one can simplify it to get F ds is equal to V into dV, dV. Now, here also you can again for a fractional conversion also, if x is equal to S naught minus S upon S naught, one can define as ds is equal to minus S naught dx, and if you substitute you get f S naught dx equal to minus v into dv. Now, you can integrate this, and the integrated form will give you the that is 0 to v dv over f S naught will be equal to 0 to x dx over minus v, or v upon f S naught, because feed rate is constant, substrate concentration is constant, and so this becomes the definite integral will come to v upon f S naught, and that is essentially v upon f is tau upon S naught equal to 0 to x dx over minus v. Now, I think again you look at the performance of a plug flow reactor, essentially ultimately arrives at the or you can transfer the S naught to here. So, tau is equal to S naught dx upon minus v, that is the reaction rate. So, essentially the performance will be almost identical to that of a batch reactor. The performance essentially will be identical to a batch reactor, and with the accepting with the difference that the reaction time here is replaced by space time, and the reactor performance therefore, on the same lines you can write as S naught x minus k dash m ln 1 minus x equal to k2 dash E naught epsilon into tau. Now, I must also mention here the term epsilon. While in the case of a stirred batch reactor, the epsilon is taken to be 1. That means, the volume of the reactor occupied by the enzyme preparation is negligible compared to the total reactor volume. Whereas, in the case of a packed batch, a significant proportion of the reactor is occupied by the enzyme preparation. Pardon? I was just trying to define the term what I have introduced here as epsilon. Now, in the case of a batch stirred reactor, when we talk, we had not considered epsilon, because the quantity of enzyme or the volume of the enzyme in the reactor is negligible compared to the total volume of the reactor. A very small fraction of the total volume is occupied by the enzyme preparation. On the other hand, in the case of a packed bed reactor, a significant fraction of the volume of the reactor is occupied by the packed bed. And the volume occupied by the fluid or the feed, the substrate, is only the wide volume of the reactor, and so therefore the volume occupied by the feed in the reactor is considered as the actual reactor volume. Therefore, this tau term is multiplied by, in fact, essentially tau, while as we defined earlier v by f, in the case of a packed bed reactor we define as tau v by f. Only thing, the tau value becomes, that means for CSTR or for a stirred batch reactor, the magnitude of epsilon is 1. So, essentially this gives you the reactor performance for a plug flow reactor using or following Michaelis-Menten kinetics. Now, the same analysis as we did earlier, if you consider for a zero order kinetics, the tau is equal to x S naught upon k2 dash E naught epsilon, and for first order you have tau is equal to minus k dash m ln 1 minus x upon k2 dash E naught tau. Now, I think it's a very important feature which I would like you to recall, that the reactor performance equation for zero order design for both CSTR as well as for PFR are identical. Now, if you look at the equation number 2 here for the CSTR, this is CSTR, and the equation for the zero order design here in the case of PFR, they are identical. That means, the fluid dynamics in the reactor, whether it is a back mix system or it is a plug flow system does not influence the reactor performance as long as the reaction is in the zero order regime or the concentration of substrate is much higher than the Km value. And I think you must appreciate that if it is in our limits, we will always like to use a very high substrate concentration. Of course, if the system does not undergo substrate inhibition, that is, if it undergoes inhibition, we have no choice other than to using a lower substrate concentration. But one will always try to, there are two things, one will always like to have a high substrate concentration for a reaction for commercial purposes. Also we will also like to have a very high fractional conversion. I mean, one would like to carry out the reaction almost to conversion levels of 95% plus, so as to achieve a product complete conversion of substrate as much as possible, and so that the recovery and purification stages are simplified, or the product stream can be used as it is for end application. So and only the difference lies in the case of the reactor performance of plug flow reactor. Now a very now if you consider, let us say, for first order regime where K dash m is much greater than S naught. Now for in the case of CSTR, you have the reactor performance as K dash m x upon 1 minus x equal to K2 dash E naught tau, or of course tau, and in the case of PFR the expression changes to K dash m ln 1 minus x equal to K2 dash E naught epsilon tau. Now if we compare the, as I mentioned earlier, that our interest will always be to have a high fractional conversion, that means most of the product, most of the substrate which is being fed gets converted into product. Now now if we want to compare the performance of both CSTR and PFR, as I mentioned, in the case of zero order regime there is no change, the performance remains identical, that means the quantity of enzyme required will be identical in both cases for carrying out, of course, the same conversion and at the same enzyme loading. But if you consider a first order regime, the performance are quite different, and if you just compare the relative performance, the relative quantity of enzyme required, that is your ECSTR, the quantity of enzyme required in CSTR and PFR, relative quantities, or we can define this term as E relative, will be equal to minus x epsilon upon 1 minus x into ln 1 minus x. The relative quantity of enzyme required in the case of CSTR and PFR under first order regime can be given by this expression. Now you notice this expression, that if higher is the required conversion level, higher is the relative amount of enzyme required in CSTR. I mean, you can just hypothetically put some values of, let us say, a safe value for epsilon for a typical packed bed reactor is, let us say, 0.5, varies from between 0.4 to 0.5. You take a simple value of 0.5, and now if you just make calculation, let us say for x is equal to 0.90, the E relative required will be equal to 4.5. That means the enzyme required for the same fractional conversion, that is 90%, in the case of a CSTR will be 4.5 times more than that required in the PFR for the same conversion. The same enzyme, the same reaction, same conversion level. The quantity of enzyme required in the CSTR will be much higher compared to PFR. Now again, if you see the effect of, if you change this fractional conversion to, let us say, 0.99, the E relative value increases to shoots up to 25. The inference basically which I want to arrive at is that higher is the fractional conversion required for a particular reaction under first order regime, significantly or drastically increases the relative quantity of enzyme required in CSTR. Basically that means, even if for certain reasons, if we want to use, let us say, CSTR, let us say pH control is a requirement, for example. If suppose pH control is a requirement and we are obliged to use CSTR, then it is always advisable only to use if the fractional conversion required is not very high. In case if the fractional conversion required is very high, if we are looking for a 99% conversion, it will be desirable to use a plug flow reactor with a partial recycle. I mean, you can have facility for pH control, of course with some inconvenience, maybe some more additional equipment has to be added, but still that will be better because the quantity of enzyme required will be much less, and that gives us a significant sort of advantage for using immobilized enzymes in PFR, and that is one of the reasons why you will notice in the literature that almost about 70 to 80% of the total reports that appear on use of immobilized enzyme, they are in a plug flow reactor, and basically the advantage lies in the quantity of enzyme required, and of course this advantage will keep on reducing, that means the relative quantity will keep on reducing if we shift from first order to 0 order. Ultimately it will reach to same quantity. You recall, if our again here if we consider that if we take the value of Km upon S0 from a very high value to keep on reducing it to a very low value, the relative quantity of enzyme will also keep on reducing, and it will become equal, or the relative enzyme, the value of E relative will become 1 when your quantity of K, the value of S0 is much higher than Km. Now, a typical profile for the relative quantity required is shown here. Now, as you notice here, whatever just I mentioned, it again signifies the same thing. That means there are two things to be looked at. One is the relative quantity of substrate to Km. In the initial stages, now here instead of Km upon S0, I have plotted S0 upon Km, well whatever parameter we measure. Now that means the top profile, the first profile indicates a very low value of S0 upon Km, which means a first order enzyme. The top profile relates to first order enzyme, that means as the fractional conversion increases, the relative quantity required also increases, and towards the final phases of the fractional conversion, the quantity very significantly goes up. The increase in the quantity of enzyme required is not very large at a low fractional conversion levels, but whereas as soon as you cross 90% conversion, the quantity required become significantly high. On the other hand, you also see when you come to S0 upon Km as 100, approaching towards 0 order enzyme, the quantities remain almost equal all through till you arrive at 90 plus or more than 95% fractional conversion. Now essentially one can have such a profile, and that is what I wanted to give you a picture that when one want to look at or analyze the reactor design, the reactor performance for any given immobilized enzyme system, one must really characterize his system with reference to such kind of profiles, so that one can get a feel that whatever is the substrate concentration required and whatever is the fractional conversion required, one can choose that where to bank upon. For example, in the earlier phases, let us say up to 90%, there is no major gain in using PFR, but if you want to use a fractional conversion much higher than 90%, then the PFR becomes more and more a matter of choice.
How do we decide at a conversion of around 0.5, which would be used?
They will be more or less identical. So then your choice should depend upon the operational convenience. For example, if the pH control is required, CSTR is preferable, and then the nature of the substrate and the nature of the enzyme, the form of the enzyme. Now, if suppose your substrate is colloidal, I think we would recommend to we will prefer to use a CSTR rather than PFR, which will choke. Ultimately the pressure drop will continuously keep on increasing. Or if suppose the enzyme particles are in the form of fibers or spherical beads, it is easier to pack them rather than putting in the CSTR where abrasion might be so for the form of substrate and form of enzyme will dictate the choice. The kinetics will not be dictating. Of course, so far we must also consider that we have not considered so far either the inhibition patterns, we have not considered how the reactor performance will be behaving if the enzyme undergoes a inhibition kinetics. That means either a substrate inhibition or a product inhibition or a third inhibitor, an external inhibitor available in that. We have also not considered the deactivation of the enzyme on the reactor performance. Now, all these parameters, particularly the inhibitors, the inhibition pattern rather, the deactivation pattern, the mass transfer requirements, the mass transfer limitations, and the non-ideal flow behavior. You see the 4 things which we have so far we have been talking assuming that all the enzyme reactors are ideal in performance and they are following a Michaelis-Menten type of kinetics. At best the extremes of those cases under 0 and first order, but we have not considered the inhibition patterns, we have not considered the deactivation kinetics, mass transfer limitations, and non-ideal flow behavior. That means we are considering only either a PFR or a CSTR, which is a ideal flow dynamics in the reactor. Now, in many cases essentially practical reactors they may not be an ideal CSTR or a ideal PFR. There might be some kind of deviations from the ideality because of the packing characteristics or some channeling taking place or some kind. Of course, in laboratory you can very easily maintain a good plug flow reactor, but in a large scale system it is always difficult to maintain, and it is always desirable to identify or characterize your reactor with reference to flow behavior and then make a correction factor when the design part comes into it. So, all these issues we will take individually rather than compounding them all of them, and because not that all the issues will be applied in a particular reactor system. We will have to identify which are the issues which are important. For example, we identify, let us say the mass transfer limitations are the most acute, the system is mass transfer limited, there is no point to consider reaction kinetics. You design your reactor system based on mass transfer diffusion requirements. Similarly, if you consider that the flow behavior is drastically non-ideal, there is a full channeling, then of course applying such system corrections have to be applied to these design expressions so as to get the reactor performance. So, I think we will stop here and continue to discuss the behavior of enzyme reactors on these patterns.